Okay, everybody, it is noon, and so we're going to get this started. Welcome to the first CEOS Mini Talk event. Thank you for attending. I'm your host today, Amy Ando. I'm a professor in the Department of Ag and Consumer Economics and co-director of the new Center for the Economics of Sustainability. We are going to have 4 short talks today. Each will spotlight key points in research and analysis of people affiliated with the Center of the Economics of Sustainability at the University of Illinois, CEOS. But we have a few guidelines just to make things run smoothly. There's going to be a lot of attendees. We're busy letting people in from the waiting room. So please keep your video off and your mic muted so that it doesn't get too busy and chaotic. If you do have a question, you can type it into the chat box where it says chat in your Zoom screen. And at the end of the talk, we'll try to answer 1 or 2 questions from the chat. We do want to thank the College of ACES and the Department of ACE for their support for CEOS that makes events like this possible. And I just wanted to let you know that if you want to sign up for future announcements, you can go to our website, ceos.illinois.edu, and click sign up, or you can email us at ceos.contact@illinois. Well, our first speaker today is me. So let's go ahead and get started. And I'm going to time myself so that we can stay on track. All right. So using nature to stop the next pandemic. We're doing this ridiculous thing, all of us in our separate homes rather than in a room in person with you because of COVID-19. And this has placed a great burden on all of us. So it raises the question, how could we stop this from happening again? Well, COVID-19 is what's called a zoonotic disease, and all that means is that it's a disease that jumps from animals to people. There are a variety of ways this can happen. There are host animals, primates and bats and rodents are common host animals, and you can get spillover directly to humans, sometimes through vectors like ticks or fleas or mosquitoes, or you can get spillover to humans through livestock, domestic animals. And so we'll be talking about that a little bit later. And then once it gets into humans, human behavior amplifies it, and then the next thing you know, you have a major disease outbreak. Well, when it becomes a major outbreak, zoonotic pandemics have killed millions of people. This here is a picture of the Spanish flu, which killed 50 million people worldwide from 1918 to 1919. This is a representation of the AIDS quilt. HIV/AIDS was actually also a zoonotic disease and has killed 33 million people so far. Continues to kill people. It's not cured yet. 690,000 in 2019 alone, and is still going strong. And of course, we are living through COVID-19, starting in 2019 and carrying on. We've had 1.2 million deaths so far. And this also, that top green line, unfortunately, is deaths in the United States. We're over 200,000, and the toll is climbing. Well, it doesn't just come from animals. Human actions have something to do with disease arrival. So outbreaks of diseases like this are fueled by things that increase contact between people and wildlife. It's not like bats and monkeys come sneak into your house in the middle of the night. We do things like deforestation that increases the edge of forested areas and brings more people into contact with wildlife that might be hosts of diseases that can spread to people. We also just have trade. That adorable little guy is a pangolin. People keep pangolins as pets. They also kill them and use their scales for traditional medicine. And so wildlife trade of many kinds is another way in which we put ourselves into closer contact with wildlife than is perhaps wise. And so this raises these pressing questions. COVID-19 is terrible. Can we stall the next pandemic by changing the way that we interact with nature? And then if we could, would the cost of those actions be worthwhile? Or would it be so ridiculously expensive that we wouldn't want to do it? Well, so we put together a multidisciplinary team to answer these questions. We wrote a paper in Science that was published in July, and this group of people is economists, ecologists, medical doctors, zoologists, and people really all over the world, in the US, in China, in Africa, in South America. And we got together to try to answer those questions, working together via Zoom in the middle of the pandemic. So there are a couple of things that we can do. Strategy number one, well, if deforestation is a problem, let's reduce it. Let's reduce deforestation. And there's been a lot of research about things that we can do to reduce deforestation, payments for ecosystem services, payments to reduce forest degradation and deforestation. And so we could use payments and policy, typo there, to cut deforestation in half in targeted tropical areas where zoonotic diseases are most likely to emerge. That's something we could do. Another thing we could do is, well, if it's a bad idea to have wildlife trade, then we could reduce wildlife trade. We could cut wild animal and meat sales, especially in China. This is a picture of a seafood wet market that was shut down in the immediate wake of the COVID-19 outbreak. This is a huge market, and that's a costly thing, but it's something that could be done. We could also enforce, we do have international policies that are supposed to restrict wild animal trade and things like chimpanzees, but they're not, the agencies in charge of that are not very well funded. And so we could provide more funding to enforce the policies we already have to limit animal trade. And then the third set of things that we could do is this sort of broad set of activities where we monitor for outbreaks and educate for prevention. So these are just pictures of some of the programs that could be supported, where scientists have networks to do strategic testing and identify that a new disease has emerged, and then stop it before it can spread and become a widespread disease. And this includes education so that there's less spread in livestock, in that livestock part of spreading from wild animals to people. All right, so how much would all of that cost? So we put our heads together. These, reducing trade of things like chimpanzees and spillovers and early detection, that's all pretty cheap. The things that are expensive are reducing deforestation, so that's about $11 billion. And ending wild meat trade in China is even more expensive. It's almost $20 billion. So a year. So that's not nothing. That is an actual cost. But then on the other side of those scales, we have to think about the harm that we incur from having another pandemic. And so if we use COVID-19 as an example, this has generated an enormous recession. You can see here, this is the 2020 recession, which has been sharper than any recent recession. And actually, recovery has pretty much stalled. And so we used an IMF estimate of lost economic activity worldwide of $5.6 trillion. And then there's the deaths. At the time we wrote this in July, I was in charge of looking at the forecast. And at the time, the forecast was that something like 600,000 people would die. Well, as you saw at the beginning, already 1.2 million people have died. But so the numbers I'm going to show you are for a conservative estimate of 600,000 people dying from a disease like COVID-19. And economists have a way of estimating the value, our willingness to pay to avoid deaths from things like disease and pollution and other things like that. So we put those things together, and lost global GDP is, between 5 and 6 trillion, and the value to us of these global mortality costs are another $6 trillion, even if we just look at a moderate estimate. So when we put this all together, prevention pays off. Oh, actually, you can't even see it over here on the right. This is the total prevention cost. So that first graph I showed you, the costs of reducing deforestation and the costs of not selling wild meat in China, you can barely even see it when you put it on the same graph as the damages that we have incurred from COVID-19. So our bottom line is that prevention is likely to pay off. So we did this thought experiment. Suppose something like COVID-19 is currently coming around about once in 100 years. Let's assume that the highest cost of prevention, so $32 billion, but and a moderate estimate of damages. So that moderate number, even totally undercounting mortality, the damages were $12 trillion. So in order to justify those prevention costs, a year of prevention only needs to reduce the chance of another pandemic like COVID-19 in the next year by about a third, less than a third. And given that this damage estimate is now, we know, woefully underestimated, the bottom line is that prevention is going to pay for itself. Questions? That's all I prepared.
Okay, so there's a question in the chat, Amy.
Great. Do you want to read it?
From Anne Finnegan. She said, is there a probability function for the likelihood the prevention measures would be effective? So how do you make that kind of an assessment about likely effectiveness of the kinds of prevention measures that you're envisioning?
That's a great question, Anne. That is something, so part of having this team of people together who are experts in all of this, we don't have a quantifiable, probability of effectiveness. It was sort of this expertise thing where they see where disease outbreaks come from, and they see that it's happening most often in the places where there's deforestation. But it's determining effectiveness, that's quantifying it, that's an area for more research. Any other questions?
I have one. How do you estimate the cost of getting rid of wild animal like meat trade? How do you get at that? How do you think about that? Are you
right? So
yeah.
That's a good question. So we only did it for China because in China there is an estimate of the value of wild meat trade because it's legal, it's sold in a marketplace. What's more complicated is figuring out what the cost would be of doing this in, say, bushmeat sales in tropical parts of Africa, where that kind of wild meat doesn't go through a marketplace. It's also more of a sustenance source of food. And through all of this, we were very concerned that these efforts not generate costs that were borne disproportionately by vulnerable people in the countries in question.
One more, if you have to.
One more question. And Madhu, if you want to go ahead, and you're next, right? Yeah, if you want to go ahead and share your screen while I answer my last question, that would be great.
Jeremy Enos asked, what is the cost comparison? Was the cost comparison, excuse me, a cost per 100 years or cost per year? What's the unit on that comparison?
We did it just for a single year. So here's the single year cost. And then you can use the change in probability of an outbreak next year. And the probability is pretty small, but then you multiply that change in probability by the damages that would occur, God forbid, if we had another COVID-19. Can you even imagine? It's just devastating. So that's how we did that calculation. It was just a single year thing. We're doing more work to think about a dynamic model, and there's more work to be done there, but this is just a snapshot that does seem to provide support for the idea that these kinds of actions could really pay for themselves. Great questions, everybody. Thank you. And now we're going to hand the baton over to our next speaker. Our next speaker is Madhu Khanna, who is a professor in the Department of Ag and Consumer Economics, and she is the other co-director of CEOS. Madhu, take it away.
All right, so we're going to turn our attention now to looking at the economic and environmental benefits and costs of biofuels. This is also done with several other co-authors, and that are both here and at Iowa State and representing different disciplines. So it's a very interdisciplinary project. So just to put this in some context, this research, it's actually being presented in 2 papers that are hopefully going to be coming out soon. But to put this in some context, biofuels are the major sort of motivation for them was to reduce carbon emissions from the transportation sector. The transportation sector has been a growing source of these emissions, and so there's interest in looking at low carbon fuels. But because biofuels are a source of energy that requires land, they also interact with other ways that we use land for agriculture. And agriculture is a major source of nitrogen leakage, which causes a number of environmental problems, notably the problem of hypoxia in the Gulf of Mexico, but also nitrogen leaking to drinking water, groundwater, having nitrous oxides, denitrification, and so on. So nitrogen is another environmental challenge that we continue to face. So in thinking about how biofuels would interact with these 2 environmental problems, and there are others, but the focus of our research is looking at these 2 implications. It's important to recognize that biofuels is not a single thing, but they can be actually produced from a variety of different feedstocks, and these feedstocks differ in terms of their carbon intensity as well as what implication they have for nitrogen. So the ones that we consider are corn ethanol, which is primarily being produced as a biofuel in the U.S. 15 billion gallons of that almost are being produced every year, and they have a potential to lower carbon intensity by 20 to 45% compared to gasoline. But corn is very nitrogen intensive. We can also produce biofuels from potentially from energy crops, and these are low input perennials, such as the ones shown on the right from our South farms here in Illinois. These are very high yielding, can be grown under rain-fed conditions, have significant potential to reduce carbon intensity, even being negative carbon relative to gasoline, and they can reduce nitrogen leaching and runoff from cropland. Another source is corn stover, which also has considerable potential to reduce carbon intensity, but high rates of removal can have a negative impact on soil fertility and lead to soil erosion. And they also may require additional application of nitrogen to replace the loss in soil fertility. So as we think about these different alternatives, we can see that there's going to be a trade-off between our efforts to reduce carbon intensity and reduce nitrogen runoff and leakage, and also be able to produce biofuels that are not very expensive, that are cost effective or competitive with gasoline. So this is just showing that some of the data, which just shows that, in fact, even with corn ethanol, there is the carbon intensity of gasoline is 94 grams of CO2 per megajoule. And this shows actual carbon intensity of corn ethanol produced in the US to conform with the California low carbon fuel standard. And that has considerable potential here, that this is lower than gasoline. Here is some of the studies, a study looking at the carbon intensity of different types of cellulosic biofuels, and again showing that these energy crops in particular can be negative carbon biofuels. And this is looking at the potential for these 2 perennial crops to reduce nitrogen runoff in the Mississippi River Basin if they were to be grown on croplands. If we were to replace 25% of the corn acres in the Midwest and the Mississippi River Basin, then you could reduce the nitrogen runoff by 8 to 10%. So large-scale production of these energy crops, particularly on corn acres, could have an impact on the Gulf hypoxia. But of course, the ultimate environmental impact of these biofuels will depend on what mix of these are actually produced. And because these are more expensive than fossil fuels, the choice of this mix is going to depend on what policy is put in place. And so in the US, we've got the Renewable Fuel Standard that was established in 2007 with various goals, one of which was to reduce greenhouse gas emissions. And it basically set a upper limit of 15 billion gallons of corn ethanol. And mandated that we should produce 16 billion gallons of cellulosic biofuels by 2022. And there was, the basic criteria for a cellulosic biofuel is it should be from a non-food based feedstock, and it should have at least 60% lower greenhouse gas intensity. So the graph here shows that we've actually met the 15 billion gallon corn ethanol mandate, which is the blue bars. But when it comes to the cellulosic mandate, we're woefully behind, and hardly begun to produce much commercially. So the purpose of this research is to do sort of a forward-looking analysis. What if we were to extend the RFS beyond 2022 all the way to say 2030, and maintain our corn ethanol mandate at the 15 billion gallon mark, and try to achieve the 16 billion gallons by 2030? What would those economic costs and benefits look like? And so in doing that, we want to look at a variety of different environmental impacts caused by these biofuels, nitrogen runoff in the Mississippi River Basin, nitrogen leakage in general from changes in land use and nitrogen application rates, greenhouse gas emissions in the US, as well as what the economic costs of this policy would be for the US agricultural and transportation sectors. And we want to separate out the impacts of corn ethanol from cellulosic ethanol. So I'm going to present results for 3 scenarios. One is a baseline. If we had stayed at the 2007 level, if we maintain this 15 billion gallons going forward to 2030, versus if we had the corn and cellulosic mandate with 15 billion gallons plus the 16 billion gallons for cellulosic biofuel, what would be the environmental impacts and the costs? And then in order to be able to compare these environmental benefits with those costs and put them all on the same playing field, we want to convert those into dollar terms as well. And so we have a method, in economics to be able to do that. So in the case of greenhouse gas emissions, there is a concept of social cost of carbon, which is the damages caused by a ton of CO2 emissions. And the value in the literature is about $50 per ton. We look at $50, and then what if it was even higher at $100 per metric ton? What would be the value of the greenhouse gas emissions saved? And we look at a variety of different changes in damages due to changes in nitrogen use. And again, there are values in the literature to look at how much of the nitrogen that is applied escapes into the environment, and what are the damages, the value of the damages that are caused per kilogram of nitrogen because of its impact on drinking water and coastal zones and so on. And so every kilogram of nitrogen, the damages range in the literature from anything close to like $5 to about $17 per kilogram. And then we want to look at what are the economic costs to the agricultural consumers, fuel consumers, and the ag and fuel producers. So when we, so this is combines a integrated approach which links a hydrological model with an economic model in order to do this impact assessment. And I'm going to just give you the sort of bottom line results that we get. So what we find is that maintaining this 15 billion gallons of corn ethanol would reduce the total greenhouse gas emissions from the agriculture and the transportation sector by about 3% over the next 15 years or so. And adding on the 16 billion gallons further reduces emissions by another 4% or so. So together, they can have a significant effect of reducing total emissions by 7% over this time period. But when it comes to nitrogen, it's a much more of a mixed story, because what we find is that actually the corn ethanol mandate, because it'll expand land under corn production, it is going to worsen the hypoxia problem. It's going to increase the nitrogen leaching by 8%. And then surprisingly, what we also found is that with the addition of the 16 billion gallon cellulosic mandate, there's actually a further increase in the amount of nitrogen leaching that would take place. So there would be another 8% increase in nitrogen leaching. And so we were sort of puzzling over why that was. And when we kind of looked into it further, what we found is that a major reason for that is because quite a substantial part of that cellulosic ethanol mandate would be met by corn stover. And removal of corn stover can have a detrimental impact on the amount of nitrogen runoff. So if for, in a hypothetical case, if we were to meet that entire mandate with only perennials, then in fact, the amount of total runoff would be lower than what we have even with the corn ethanol mandate. So we might actually begin to offset the damages due to corn ethanol. Or if we reduce the amount of nitrogen, replacement nitrogen applied to corn stover, we could also reduce the amount of runoff. But without those constraints, there'd actually be an increase in the problem of hypoxia. Then we added up all the other nitrogen impacts as well, and I'll get to that in a minute. But so here we looked at what are the total economic impacts across different sectors, looking at the agricultural sector, consumers, producers, and transportation sector, and so on. And what we find is that, with the corn ethanol mandate, the key group that benefits from that is the agricultural producers, and that's largely because the mandate raises the price of food crops. And correspondingly, there is a cost to the agricultural consumers who have to pay higher food crop prices. Of course, this is much smaller with the addition of the cellulosic mandate, because that has a much less negative impact on food crop prices, and therefore has a lower benefit for agricultural producers, but there is still a benefit to them. The cost of the mandate in terms of is borne by the fuel consumers, and so that's sort of the negative here. There's in the current model, there's not too much of a negative impact on the fuel producers. Looking at the environmental benefits, so there's a benefit in terms of greenhouse gas emissions, larger in the case of the cellulosic mandate than the corn ethanol mandate, and nitrogen damages, which are really significant in the case of the corn ethanol mandate. So at the bottom line is that both mandates impose net costs on the economy, taking into account both economic and environmental consequences. These costs are much larger with the corn ethanol mandate, and but negative also with the cellulosic mandate. So what does all that mean? Well, what that implies is that, there's several factors here that affect, this is one estimate, and we look at a variety of different other scenarios. But in general, what we can sort of take away from this is that these biofuels do have a potential to reduce greenhouse gas emissions, but their overall costs and benefits will depend on a number of different factors. A key one in that is going to be the price of oil. As the price of oil is lower, the greater the cost of trying to impose higher cost biofuels on the economy. In the case of cellulosic biofuels, which are still under production, and their commercial competitiveness is, we're still to get to that point. What technological improvements take place will also influence the ultimate economic cost of using them. And then the value that we associate with the emissions reduction and the nitrogen damages that are caused will also impact how much we value overall having biofuels in the mix of fuels.
It's time for our next speaker. So Hope Michelson is an associate professor in the Department of ACE, and we're going to move back to a global perspective. Take it away, Hope. I think you're muted.
Muted, but you can see the slides, yeah?
Yeah, we can see the slides, yeah.
And my extremely tidy desktop too.
Put it on full slide, there you go.
So I'm going to take this global perspective, and I thought it would be fun to use this short talk as an opportunity to think about a big issue and to sort of set the stage and then talk through some implications of current trends in this space. So I'm going to talk about small farmers and global value chains, and the degree to which and under which conditions that engagement of the poor, in particular small farmers, in global agricultural trade can actually sort of be attentive to or relate to or meet the goals of sustainability that we seem to have and that are still emerging. So about 75% of the world's poorest people, so this is people living on less than $2 a day globally, live in rural areas and rely on agriculture for their livelihood. So when people ask me why I study agriculture, it's because I'm a development economist, it's because I'm interested in poverty, and rural areas and agriculture continue to be the sector and the regions that sustain the poor, right? So in particular, as economies develop, we see again and again a trend in which the industrial sector and the service sector of the cities sort of grows faster for a number of different reasons than rural sectors, in terms of the sort of especially the productivity gains and labor employment. And so rural areas end up being this sort of reserve, this like sink of poverty as economies change and grow. So this is this persistent challenge that economies face as they grow and as they restructure. So the World Bank currently estimates, it's a couple years old, but it hasn't changed that much. Globally, there's 500 million small farm households, so that's times 5, so about 2.1 to 2.5 billion people, right? If you've got a number of people in those households. So these are small-scale farmers cultivating less than 5 acres. One thing that's really interesting about this sector is that we don't tend to know about the specifics of its geography, actually. So where small farms are located is known kind of in a broad sense, but in terms of the specifics, we don't always understand. We have really good data about rich people. It's something I always like to say. We don't have very good data about poor people, right? So this is a nice paper that was done by Minnesota, some researchers at Minnesota, looking at using census data and ag census data to sort of figure out, okay, where are the really small farms, right? Where are these sort of very small, medium farms, right? To sort of get really specific about the geography of these places. So you can see, right, these parts of Southeast Asia and East Asia have a lot of very small farms. This is less than 2 hectares, and that's for different reasons related to history and sort of land tenure policies. And then you've got a lot in Central and Sub-Saharan Africa that are medium and small. Okay, so widespread and important. So, but this population is really important from a sort of ag development perspective, but also from a broader perspective. And we know this is from a World Bank development report from a few years ago that focused on agriculture. Right, that increasing agricultural productivity is fundamental to restructuring and developing an economy and reducing poverty, right? So we know that the poor tend to be in agriculture, and we know that increased productivity in the ag sector is associated with, not necessarily causally, but there's a strong association with reductions in poverty, right? So this is really important from a global perspective, from an individual country's development perspective, right? If you care about poverty, you need to think about these issues as well. Okay, so the other thing that's really fascinating here is that small farmers are fundamental, right? There's tons of them, and they tend to produce commodities in many cases that are really important to the global economy, but we don't see them. They tend to be economically invisible, and I can be specific about what I mean by that terminology. So, there's this interesting distinction with ag that makes it really important and really I think fascinating to think about in terms of why it's different from other sectors of the economy, right? So agricultural production has a specific location requirements associated with it, right? Geographic and climate constraints that mean you have to grow particular crops in particular regions of the world unless you want to spend tons of money on greenhouses and irrigation and stuff, right? So if you want to sort of economically cultivate crops in particular, you're going to have to do it in particular environments. So you're sort of, you're kind of forced to source particular crops from particular regions of the world. And in many of those regions of the world, small farmers are fundamental to the production of those crops, right? So you have to think about this problem if you're somebody who's who's sourcing cocoa, for example, coffee, cashew, cotton, right? These are crops that are grown by the poor, and they're grown in particular places, right? In particular low-income countries. So that's something that's really important. So what do I mean by this invisibility? So small farmers, this is a kind of a schematic from a report done by a sort of large chocolate foundation on the cocoa supply chain, right? So small farmers sit at the beginning of these long global supply chains for products, right? So you've got smallholders, and then you've got multiple levels of sort of market intensive, intermediaries sitting between smallholders and then initial stages of processing, retailing, wholesaling, and consumers. The production tends to be geographically dispersed and pretty fragmented, and that has these interesting consequences related to, you know, sort of limited quality incentives within the supply chain and sort of limited economic visibility. So, but at the same time, right, so you've got this fractured production of commodities which are being grown by lots and lots of small, poor growers all over the world, in the context over the last 40 to 50 years in which agricultural trade is rapidly expanding. We've got increased economic integration, lots of sort of, you know, decreases in information and transport costs, and increased sort of economic integration through, you know, multilateral trade negotiation, for example, right, happening. And then global value chains are getting more sophisticated. So you've got new product standards, you've got process standards, you've got third-party certifications, and increased traceability for food safety, right? So we're talking about organic production, we're talking about environmental practices, you know, bans on child labor, fair trade. So tons of stuff happening in this sector, right, related to increased consumer sophistication and increased consumer demands for attributes that we think of as being related to this definition of sustainability, right? So these are attributes that I would argue embody a current definition of what sustainability means, right? We've got ideas about labor standards, environmental standards, process standards, right? So this is a part of, I think, the current incarnation of agricultural sustainable supply chains. And so that's really interesting, right? So you can think about, all right, what does this version of sustainability mean for small, poor farmers? So I think there's a big problem here. And I have research on this, and I'm involved in other research, and other folks are thinking about this as well. Right? There are these fundamental challenges of small farm production and marketing, especially in low-income contexts, where you've got uninsured production and price risk that people are facing, high transactions costs, poor infrastructure, limited credit, limited legal enforcement of contracts, small scale production, right? So those are challenges that raise the costs and the risks of buying from small farmers and contribute to their exclusion from these kinds of supply chains, right? And as we're putting in some of these new process standards, there's good evidence that, right, small farmers cannot afford to get certified. Small farmers, if you're worried about child labor, are a bad bet because they're going to rely on family labor for harvesting. So there's a way that these process standards and these new kinds of sustainability standards seem to be going even further in terms of the potential to exclude small farmers, unless you've got kind of third parties getting involved. And I can talk about that. It's kind of an interesting set of relationships. So I've done a lot of work also on contract farming. So in contrast with these sorts of standards programs, contract farming can and seems to be more able to address these kinds of challenges and may be a more sustainable way to actually engage and benefit small farmers in these kinds of opportunities. So I think that's really important. I think we need to think about what current sustainability standards actually mean for the sustainability of the supply chains as they exist, right? And there's evidence that the current system is failing small farmers and their global buyers. So I'm going to give you one sort of example of this before I wrap up. There's this interesting initiative that was kicked off by Mars about 3 years ago, which is a collaboration across a number of very large buyers, international buyers of global agricultural commodities. And what they're worried about is that, in particular in coffee and cacao, prices and incomes are historically low. They're extremely low over the last couple of years. And these global buyers are looking at the current circumstance and saying, wow, our supply chains may not be sustainable economically in the long term for us as buyers. They're worried about the exit of the poor from the production of these kinds of commodities. And they're worried about facing, in a couple of years, a circumstance in which they do not have sufficient supply at a price that they want to be paying for these commodities. So I think that's really, really interesting, right? Because we have a world in which we've got all these sustainability standards proliferating, and at the same time, we see concern among the big buyers and among small farm groups as well, that the current system is not working in terms of providing sufficient income, lasting income, and lasting incentives for production of these commodities. I think that's a really important dynamic. So I'm going to wrap up on the next slide. So my closing thoughts then, I think most sustainability standards are solving problems for consumers. They, in fact, may create new costs and exclusions for farmers, especially the kinds of farmers that we might be really prioritizing and wanting to engage in the process. we need to understand, and there's a lot of work going on in this space, but I think we need to really, think about it in a particular context. We need to understand what the current standards can actually achieve and understand the conditions under which small farmers can participate and how they benefit, and what the broader effects of these initiatives are on labor, which is a completely unstudied aspect of these supply chains. We don't see the laborers. The laborers tend to be even more marginalized and poorer than the growers, and rural inequality. And I think there needs to be some really careful thinking about what global value chains need to be in order to actually be sustainable for the growers. And that means economic visibility for the farmers. As I said, I can talk about that a little bit, building of economic identities, so they can access credit and insurance. And then I think thinking about how to address systemic market failures that are often embedded in and furthered by existing policies that small farmers face. So.
Great job, Hope. And I think it just points out that when we talk about sustainability, it isn't just about the environment, it's about the people in the system, and especially worrying about vulnerable people who are already struggling. Okay, so we're going to be transitioning to the next, to Yilan's presentation, but do people have questions for Hope? I guess there was a comment in the chat that we see something from Christine Bozak. We see something similar in the US with small farms being unable to get certified USDA organic. Have you been part of conversations about that?
No, I'm really interested in starting to think about these issues in the domestic space. And that's one thing that I'm excited about with respect to CEOS, is taking some of the insights on the work that I've done in an international context and thinking about the way that that maps into the kinds of constraints that producers face in the United States. So I think there's some real similarities.
Yeah. Can you give an example of a particular, you said you thought contracts would be a better, potentially better strategy. So what's an example of that for this?
That's great. So there's
don't study that. Yeah.
Right. So there's ways that you can have contracts that provide farmers with sufficient certainty about the quantity and the price that they're going to be, the quantity that they're going to transact and the price they're going to be paid, that we see significant increases in the investment farmers are willing to make in the production of that crop. So you've got farmers producing in markets that are highly fractured and highly unspatially integrated, which means when you have a big local harvest, it crashes the price. Right? So if you have well-integrated markets, if you have a big local production boom, that gets sort of arbitraged out spatially across lots of other markets. But lots of places that doesn't happen. And that leads to these sort of boom and bust cycles for farmers. So we see some success in contracts that come in and say, okay, listen, here's the price you're going to get, guaranteed. And then once you've got that, you see that farmers are much more willing to make investments in the production. And those kinds of investments lead to higher productivity, changes in labor productivity, lots of other kinds of effects that have broader transformative effects on rural sectors. So.
There were a few more comments in the chat, but I think we need to move on to Yilan. So Hope, if you want to respond to the comments in the chat, just in the chat, we're going to turn to our fourth and last, but certainly not least, presenter. And who knew which 4 talks would emerge today, but it's fun to me that they're all so completely different. So Yilan Xu is an associate professor in the Department of ACE, and she's going to be talking about some research that she's been doing on fracking.
Thank you for the introduction, Amy. I realized that this is an interesting time to talk about fracking now that we are less than a week away from the presidential election. But I want to make a full disclosure that this talk is based on 2 research projects that were conducted a few years ago. And one of the papers has been published in a journal, and the other one is under review. Okay, so the purpose today is to introduce some research highlights from these 2 projects without necessarily get into super technical details. Okay, so what is fracking? So fracking is the technology that injects liquid at high pressure into rock formation to release oil or gas. It is a well stimulation technology to enhance productivity. You might have already known that, but you might be surprised that this technology is nothing new. It began in 1949 in the United States. What's new is the horizontal drilling. As you can see from this figure here, it increases the well's contact with the reservoir. So the combination of fracking and horizontal drilling makes it technologically and economically feasible to extract fossil fuels from shale formations. So then from this figure, you can see that wastewater is a byproduct of fracking, and you can see the trucks are involved in this process. So I have two research questions related to these two facts. The first one is, does fracking produce more wastewater? The other one is, does fracking related trucking cause more fatalities? The short answer to the first question is no. The short answer to the second question is yes. So in order to study wastewater, we pulled together a sample of onshore oil and gas wells from 17 states where they report the wastewater discharge month by month. From the data set, we don't know which wells apply fracking technique, but we do know which ones are horizontal and which ones are on shale formation. So in this research, we define those that are both horizontal and on shale formation as the unconventional oil and gas wells. And as I mentioned earlier, those are the ones that are more likely to use fracking. And then we also define all vertical wells as a conventional oil and gas well. So then from these first two figures, you can see that both the total volume of wastewater discharge of unconventional wells and the total number of unconventional wells have been growing over time in the past decades. But this is at the aggregate level. If you want to look at per well wastewater discharge, you will see that the per well wastewater discharge of unconventional wells exceeded that of conventional wells in 2014, and it has been higher since then. Although some people might feel compelled to conclude from this figure that unconventional wells produce more wastewater, this is not yet the whole picture. I want to bring to your attention that the share of new wells is always higher for unconventional wells than for conventional wells. And why does that matter? Because studies have shown that for unconventional wells, 20 to 50% of the first 10 years cumulative wastewater is generated in the initial 6 months. So separating those new wells from old wells is super important. So our goal of this study is to disentangle the lifespan effect and the cohort effect to understand the magnitude and the dynamics of the wastewater discharge of unconventional wells. Now, why does cohort matter? Because there has been consistent upgrades in fracking technology, which may actually make it more efficient. So let's look at what we found. We used an econometric model that compares the discharge month by month into their lifespan, controlling for resource type, the dominant product type, the energy production, and the local geology. Here I provide you 3 snapshots in time, 2008, 2011, and 2014. There are 3 findings here. The first one is that unconventional wells monthly discharge is more front-loaded over time, as you can see, moving from left to the right. But within each figure, you can see that the monthly discharge actually decreases over lifespan. And it actually becomes lower than conventional well discharge at some point. Then next, we look at the cumulative wastewater discharge. By cumulative, I mean the discharge up to a point in a well's lifespan. So from these 3 figures, we can see that unconventional wells cumulative discharge becomes lower than a conventional well at some points. And the break-even point is delayed for more recent cohorts. By break-even point, I mean the time into the lifespan when an unconventional well has the same cumulative discharge as a conventional well. Okay, here I also want to point out that the average lifespan of an oil or a gas well is 20 to 30 years. So the break-even point will be reached before the life ends. The last thing we look at is the wastewater to energy ratio. Here you see the negative gap between unconventional wells and conventional wells. And this can be interpreted as the efficiency advantage of conventional wells over, unconventional wells over conventional well. So from these three figures, we can see that unconventional wells are more efficient in the entire lifespan since day one. And then we can also see that fracking has become more efficient over the time as the growing gap that can indicate when you move from left to the right. Okay, so here by more efficient, I mean more energy is produced for a given unit of discharge. So the three major takeaways from this wastewater study is that an unconventional well eventually discharges less cumulative wastewater than a conventional well. And it always produces more energy given 1 unit of wastewater discharge. And fracking technology is getting more efficient over time. All right, now build on this finding that fracking wells produce an intense amount of wastewater in its early lifespan. Next, we want to study whether trucks used to haul wastewater cause more fatal traffic crashes. Now, from this figure, you can see that the growth in fracking wells in North Dakota coincided with an increase in fatal crashes, especially the truck-involved crashes. If you look at other shale formation regions, the same thing is happening. But as an economist, we can say this is causal, right? Because we are looking at regional data. During the same period of time, there are also more migrants moving into the region, and there are also more commuters on the road because of the growing production in the region. And these factors are not necessarily directly related to wastewater hauling. So what we did was to do micro-level comparison across row segments so as to get around common shocks to the region, but also control for local differences. So for each row segment, we count the number of crashes in a given month, and we also count the number of wells at various production stages within the 6 miles of a row segment. So that we can then disentangle the effect of different production procedures. Here, by doing this comparison, we find that it's the post-fracking stages that matters a lot, which then is associated to the wastewater hauling. We find that one more post-fracking well within 6 miles of a row segment caused more fatal crashes by 8% and increased the accident severity by 7%. Okay, so the combined findings from these two studies call for an adaptive and dynamic regulatory system. This is because technology is improving. What used to be a problem at some point of in the history might become less of a problem or no longer a problem as the technology develops. And meanwhile, fracking also has a distinct production cycle. So a problem at some point of its life cycle will eventually disappear as the well matures. Another point we want to make is that sustainable infrastructure investment could be very critical. Local governments may want to develop a long-term and forward-looking perspective to account for technological improvements as well as the growth in the production scale. Thank you. Any questions?
That was right on time. Great job. Yeah, any questions anybody has? So while people think, I'm just curious. So this is great. When you hear people saying, we need to ban fracking, or no, it's going to save the world, given that you've done all this research, where do you come down on what our policy should be?
Right. Yeah. Okay. That's a great question. And our findings by no means imply that we should totally ban fracking. And actually, based on the finding list, a lot of things that the local government can do. Take the traffic paper, for example. Instead of totally banning fracking in the region, local government can think about regulating the timing of fracking across wells, right? So that they will not all happen at the same time to create traffic burden. And they can also redistribute the traffic loads over time, because one of our findings that I didn't have time to explain is that we find that most of the increases happen during the daytime rush hours. So there's a potential to, reallocate the traffic loads over time. And then they can also create a system that resolve a truck lane, just in the idea of the HVO lane, right?
Right.
And then they can also create a traffic alert and warning system that can help people get oriented. So there's a lot of things that can be done based on the research findings, other than totally banning.
Yeah. That's great. So one last quick question. Why is the break-even point delayed for more recent wells?
I think it's because it's getting, as we showed, that more upfront loaded. So the gap between between the unconventional well and conventional well is getting bigger and bigger for the initial 6 months. And that is resulting in the delay. But as I said, the lifespan averages from 20 to 30 years. So at some point, eventually it's going to result in a lower total wastewater discharge. And also, I want to highlight that unconventional wells tend to produce more energy at each point of time. So if you look at the energy efficiency, it's actually higher.
Great. Awesome. Well, so thank you for attending, everybody. Thank you, Yilan and Hope and Madhu, for your great talks. Our next mini talks, CEOS mini talks, is going to be lunchtime on December 2nd. To receive announcements, I put our email and our website in the chat. Email us at ceos-contact@illinois.edu, or you can sign up on our website, ceos.illinois.edu. If you arrived late and missed part of it, we recorded this and we will be posting these little talks on the website. Spread the word, tell your friends, and we'll see you in December. Bye, everybody.
Thanks. Bye, everybody.
Thanks, everybody. Thanks for coming.
Bye.